Uh, let's get into it. So I think we can start now. So for formally, welcome everyone to another gathering of the community of practice in sustainable concrete, proudly hosted by Smartgrid CRC. I am Arun. I work for Advanced Precast, and I'll be your host today. Before we start, in the spirit of reconciliation, we acknowledge the traditional custodians of country throughout Australia and their continuing connections to land, sea, and community. We pay our respects to elders past and present and extend that respect to all Aboriginal and Torres Strait Islander peoples today. Smartly CRC, as many of you would know, brings researchers and industry and government together to turn sustainable concrete research into practical solutions for infrastructure. These sessions, like community of practice, are about discussing and sharing those ideas, practical challenges, and exploring what sustainable concrete looks like in the real world. Today's session is on sustainable low carbon concrete for future concrete infrastructure. You have a dad joke about low carbon concrete, but I wasn't sure it would set well with everyone. So let's get to it. I googled this earlier. Australia uses more than 26 million cubic meters of concrete each year. So any improvements in the material selection, mix design, and specification can make a very large difference towards the decarbonization pathway. Um, so this project is one of such, is looking at how we can reduce emissions by using alternative materials as partial replacements for conventional cementitious products and also natural aggregates. Um, this looks across the board, including recycled and waste-derived materials that would otherwise be landfilled. Uh, this is basically the engineering version of putting concrete on a diet. Um, what makes the topic especially relevant is that this is not just about the lab scale ideas. It is about how research, transport agencies, and industries can work together to build the evidence and confidence needed for broader market adoption of low carbon concrete. A few housekeeping uh, rules before we get to it. Session is being recorded and will be shared with the registered attendees. Kindly ask to keep your microphone off while the presenters are speaking. We'll hear from each speaker in turn and then open the floor for questions. Having said that, if you have a question during the presentations, feel free to put it in the chat. Hold it for the Q&A. Uh, we are fortunate to have two excellent speakers with us, bringing complementary perspectives from specification, infrastructure, delivery, and research. Um, so the first speaker, Wayne Roberts. Wayne has 35 years of experience as a structural and civil engineer, started way long before I was born, with a strong focus on bridges and heavy industrial structures. For the last 23 years, Wayne has worked for the Queensland Department of Transport and Main Roads, preliminary focusing on concrete, precast concrete, and concrete technology, and more recently on bridge design, the construction, and decarbonization. He's also a member of a number of concrete materials and concrete design standards committees representing Austroads and Engineers Australia. Wayne, thank you for joining us today. The floor is yours.
Thanks, Aaron. My role today is really just to provide a bit of context and introduction to Rebecca's work and Rebecca's presentations. First item, I guess I work for TMR in Queensland, but this research has primarily been sort of funded or supported through Smartcrete by Austroads and Transport for New South Wales. So we acknowledge their involvement and contributions into this program. As Aaron sort of started to introduce, we're all aware of the requirement for, sustainability and circular economy and decarbonisation when it comes to concrete. And, most road authorities are certainly on that path or on that journey as well. A bit about what we see or what we look for when we're looking at alternatives or alternative materials or other solutions. I guess the first thing we're typically looking for is equivalent or better performance. So we're looking for solutions and materials that offer similar or better performance. We're not generally looking at solutions that don't sort of tick those boxes. Another thing that we're looking for is the solution has to be scalable. So it can't just work in a lab scale or 300 or 400 litre concrete mix. The solutions that we look for have to be scalable up into multi millions of cubic meters or they need to work at scale or be viable at scale. Another attribute that we're looking for is it's got to be economically and logistically viable for the supply chain. So if it doesn't work with our if our concrete suppliers or our traditional supply chain can't make it work economically or logistically, then it may or may not take off in the future. So I guess we're always looking for solutions that tick that box. And I guess the other sort of criteria is typically, we need to be able to have some measurable attributes to write into a specification or for either the material supply or the concrete supply. So we need something that we can measure to manage the quality and the sort of performance attributes. We can't just have a sort of written description that sounds nice, or if we've got something we can measure, then that makes it a lot easier. So that's sort of some key sort of things about the alternatives we're looking for. In terms of how we sort of look to implement it, we typically go down a bit of a risk management approach. So stage one is usually some investigation sort of research. And then we typically might move to a small scale trial or a larger scale field trial. And then we sort of typically look then to introduce it into N-class concrete or normal class concrete, which is our sort of lower spec concrete in our typically 50-year design life. And then we sort of step from that up to our S-class concrete, which is sort of our 100-year design life type bridge type concrete. So for example, some of the things we're looking at today in today's presentation, we've sort of into the N-class concrete, but part of the research we're looking today is to what do we need to do to step up to S-class concrete. And so the things that we're sort of focusing on today that Rebecca's going to look at is, one is the bottom ash, which is a solution to sort of the high grade, or an option rather, to the sort of high grade fly ashes, and recycled aggregates is the two sort of main features of what we're going to look at today. So I think that's it from me, Aaron, and back to you.
Thanks, Wayne. That's a nice overview of what from an infrastructure point of view, and how the problem is looked at and how the problem is managed, especially the risk is managed in identifying the opportunities. Thanks for that, and that nicely takes us to the second speaker, who's Professor Rebecca Gravina. Professor Rebecca Gravina, a short bio, is she's in the Department of Transport and Main Roads, Chair of Structural Engineering at the School of Civil Engineering at University of Queensland in Brisbane, and a leading expert in the performance, durability and decarbonisation of concrete infrastructure. With more than 25 years of academic and consulting experience, she advances innovations and sustainability and rehabilitation of reinforced and pre-stressed concrete infrastructure through research on low-carbon concrete, high-strength reinforcement, fiber-reinforced polymers and recycled materials. Her research has influenced national and international standards, strengthening infrastructure resilience and supporting the circular economy. Her co-authored textbook, Pre-Stressed Concrete, supports education and practice in sustainable design. Professor Gravina is Editor-in-Chief of the Australian Journal of Civil Engineering, a Fellow of Engineers Australia, a certified and registered professional engineer, Executive Director to the Australian Certification Authority for Reinforcing and Structural Steel, and a member of the Executive Committee of the International Institute for FRP in Construction. Rebecca, thanks for being with us. Over to you.
Thank you, Arun. I'm just going to share my screen and then commence. Let me know if that is not working. And I'll just bring that over here for a minute. Is that working? Yes?
Yes, it is working. All good.
Okay,
Yeah.
good. And so thanks, Arun. Thanks to Smartcrete CRC for inviting me to speak today, and also to Wayne for his time to introduce our joint project, and his support is acknowledged as well. So as Arun said, I'm a Professor of Structural Engineering in the School of Civil Engineering at the University of Queensland, and it's also a position that's related to the Department of Transport in the school. Before we start, I would just like to acknowledge the traditional owners and the custodianship of the lands in which we meet, and pay our respects to their ancestors and descendants past and present, and we recognise their valuable contributions to Australian and global society. So the focus of today's presentation is really to provide you an overview of the work that we've been doing that's funded by Smartcrete CRC, by Austroads, and also with partnership for Transport for New South Wales, TMR Department, Ash Development Association of Australia, and also our joint research partner in RMIT. And also like to acknowledge our two PhD students that have been working on this project, Mr. Hashen and also Jessica, and also Associate Professor David Law and Associate Professor Vin Dow, from one from RMIT, the other one from UQ. So we have quite a good group of researchers involved in this project, and we meet quarterly with our industry partners as well to get that continuous feedback. So the project here really focuses on the development of sustainable low carbon concrete for future infrastructure. So for new builds is what we're really talking about. And we're looking at how we can reduce environmental emissions from concrete by using alternative materials as partial replacement for cementitious material, and also for natural aggregates. The waste streams are from industrial, commercial and domestic sectors. And as I've already said, this project's part of that CRC program. The significance of this particular project, and there's been a lot of work done over the last, especially there's been quite an influx over the last 5 to 10 years of research work into using recycled materials in concrete. But the significance of this project is that we are looking at combining more than 2 recycled materials in one concrete mix, and we're trying to provide recommendations that fit a target strength of minimum of 40 MPa, and to fit specifications required by different departments in terms of meeting concrete fresh and hardened properties, and also concrete durability properties. So we really do try to cover the full spectrum of the performance requirements needed for concrete pavement materials. And I suppose what's interesting also is that we are looking at addressing, well, what happens with our fly ash when it runs out, and so typically the dam ash that is used over time is a well accepted material from coal combustion, as coal combustion is no longer a primary process here in Australia. That bottom ash at some stage will have a design end life, and we're looking at, well, not the bottom ash that's typically your fly ash sort of type grade. Well, how about the stockpiled bottom ash that usually doesn't get looked at? So our research here is really looking at how can we use stockpiled bottom ash, and what potential does that have in our concrete mix designs also. And I mean, this is probably a schematic that most people are familiar with about the sort of life range of where fly ash is at, where our ground granulated blast furnace slag, lithium products. There's other research of people doing looking at lithium byproducts as a SCM. So the dam ash or stockpile bottom ash is what we're looking at in this case, and other types of materials. In terms of the DOT standards, and sorry to anyone that's here from Western Australia, but I've just sort of put here the Eastern Board at the moment, DOTs, and in terms of recycled material content for aggregate replacement, Transport for New South Wales has recommendations there for crushed glass, but crumb lumber and recycled aggregates is not covered at this point in time. In terms of cementitious binders, fly ash has been well accepted across the board for a long period of time, and so has the ground granulated blast furnace slag fly. So, but furnace bottom ash is not covered yet in those codes. So, and I suppose.
Excuse me, Rebecca. We can still only see your first slide.
Oh,
we're still on the project overview slide.
Yeah. Oh, thank you very much. So in terms of project significance, I was just talking about this table here, where we're talking about the different DOT specifications and what materials are covered, and also I was showing here the slide that's to do with the sort of the roadmap in terms of where our industrial byproducts can be used for SCM material. In terms of this project, this presentation will provide listeners with a nice overview of a framework that can be adopted in terms of working from an understanding of what the recycled materials are that are available, how to characterise those recycled materials based on different requirements, how to go about determining an optimised concrete mix design for specific performance parameters such as the plastic and hardened state, what's required in terms of the mix design optimization for durability requirements, and as Wayne said at the start, developing mixes that can then be upscaled and field trialled as well. So that's one of the deliverables in this project. The environmental and financial cost assessments also needs to be done in parallel with this work also, and then hopefully this research will be able to inform concrete with recycled material content in terms of specifications for design. So where we are currently at with this project, we're up to the field, just at the end of the durability assessment work and up to the field trials. So this gives you a good view of the materials that we're using in this particular work. So the binder types we're looking at are general purpose cement, fly ash and stockpiled bottom ash, all materials that are locally sourced and easily available. For the fine aggregate in our concrete mixes, obviously we're dealing with natural sand and also man sand, which is typically being used in concrete mixes for probably 20 years or so anyway, but we've also looking at how to add in recycled crushed glass to our optimised mixes, and replacement of coarse aggregate, so 10mm and 20mm with recycled coarse aggregate, again in the 10mm and 20mm size range. Also important when you're doing your mix designs to have an understanding of what the specific gravity of those materials are and how they are, how they relate to the natural material that would typically be used. So that's provided here. Also, in terms of the material sourcing, we've worked with local suppliers. So we've got a test program that's working in both, mainly in Queensland, a little bit has been done in Victoria also, in terms of, but what you're seeing here is the Queensland suppliers for the local material sources. So our stockpile bottom ash is coming from close to Rung, which is close to Gladstone. Our our coarse aggregates locally sourced, even, and our recycled concrete aggregates also locally sourced, as well as the crushed glass material. When it comes to the material characterization for the stockpiled bottom ash, the properties that we're interested in is to understand the morphology of the material, the specific gravity, the particle size distribution, what's the chemical composition, and do an analysis for that. What are the different crystalline phases? So we've also the moisture content, loss of ignition, flow, and the strength activity index. So and it's quite clear here what test method that we've followed and what procedures that have been adhered to. For the recycled crushed glass, the material characterization, it's important for this to, in addition to look at the chemical composition and the particle size distribution, also to understand the sugar contamination and what the chemical leaching properties are, and what influence does the recycled crushed glass have on ASR. So that helps you to decide what particle size you'll want to specify when you're dealing with recycled crushed glass in your concrete mixes. In terms of the recycled crushed aggregates, particle density, water absorption, the flakiness tests, the aggregate crushing value are all very important, as well as the different constituents that make up the recycled concrete aggregate. So it's very important that the type of recycled aggregate that you use has is strong enough and can fit the properties and requirements that are needed, as well as that particle size distribution. We'll talk a little bit more about that also. So when looking at the stockpile bottom ash, we have done an SEM analysis to investigate the particle morphology, and these results show that the stockpile bottom ash particles are porous and irregular. The XRF and the XRD analysis were carried out to investigate the chemical composition, as well as the crystalline and amorphous phases. And what you can see here is that the chemical composition between the fly ash and the stockpile bottom ash are quite similar. In terms of the XRD analysis, we can see that the stockpile bottom ash has 61% still in the amorphous phase, as opposed to 39% in that crystalline phase. So the more amorphous percentage that you have, the more reactivity of that material will be when we are looking at developing the concrete mixes. So look, it is a little bit less the stockpile bottom ash than what we would experience with the fly ash, but there is some ways we can work around that. And also the specific gravity of the stockpile bottom ash is slightly lower than that of the ash. However, that particle size of the stockpile bottom ash is much larger, as you can see from this top right-hand graph, but the size range is a little bit closer to the sand, and so having that particle size a bit larger in the stockpile bottom ash sort of led us to that next phase where what do we do in terms of potentially grinding the stockpile bottom ash using a ball mill. So that was the next step that we followed was, well, if we looked at using a planetary ball mill to grind that stockpile bottom ash for specific periods of time and try to optimise our mortar mix designs. And we started with a control where we had just your normal cement. Then we had a ratio of fly ash added to the mix design, and then we ran the ball mill for either 15 minutes or 30 minutes, and then added then increasing amounts of stockpiled bottom ash. And we found that the combination of stockpiled bottom ash at about 75% replacement of the fly ash in the mortar mix gave us an optimum amount that was close to our control, and also gave us a particle size distribution close to what you would expect with the fly ash as well, to try and control that performance. So there are ways that we can work with the SCMs to improve its reactivity in our mixes. In terms of the have I missed? No, that's right. In terms of the recycled crushed glass, this is some of the results that we have achieved in terms of the characterization for the apparent density, the dry density, also the water absorption properties, and how that compares between the recycled crushed glass, the manufactured slag, and the natural fine sand. Other work that we've been doing is in terms of the ASR, alkali silica reaction performance of recycled crushed glass at different percentage replacements of within the mixed designs up to 50%, and also the leachate properties of the material also. So that's helped us inform up to what percentage replacement we will put recycled crushed glass into those mixed designs. In terms of the recycled crushed aggregates, the first thing we looked at was what is the constituents of those recycled crushed aggregates, because we're very interested in the we are very interested in the aggregate crushing value, because if the aggregate is too soft, then it's going to really impact the mechanical performance that we will achieve. And also these constituents, normally the recycled crushed aggregates are a combination of rubble and brick, and also a recycled concrete itself. And provided that recycled concrete content is as much as possible, is as large as possible, you can guarantee quite a good quality product of that recycled concrete aggregate. There are some supplies of construction and demolition waste that are not suitable to be used for concrete with these sort of target strengths of 40 MPa and above it. So that's why this material characterization is very important. And also the particle size distribution to get a nice packing performance through, or particle packing performance through our mixes. In terms of optimized mix designs, we started with a control mix that satisfied the DOT's requirements for an N-class grade concrete with a minimum target strength of 40 MPa. And with certain amount of general purpose cement and fly ash, man sand, natural aggregates, fine aggregates, water reducers and retarders in the mix design. The Portland cement to SCM content ratio in the mix we adopted was 68 to 32% by volume. And then we adjusted this control mix design to add in increasing amounts of fine aggregate replacement, coarse aggregate replacement, and also a fly ash replacement. So we kept the cement content the same, but gradually reduced the fly ash and increased it with bottom ash. So what you can see, and these are two optimized mixes, OP1 and OP2, that we have sort of honed in on, but prior to that we carried out a full Gucci analysis where we looked at different combinations of permutations of different percentages of glass in the mix, 10 millimeter recycled aggregate, 20 millimeter recycled concrete aggregate, and then also the bottom ash. In terms of the fine aggregate, we have a we have about 64% replacement of natural sand with recycled crushed glass and man sand. In terms of the cement, as I said already, 68 to 32% by volume comparison. And of that, of the SCM content, the majority of that is 75% of that SCM content is bottom ash. The other 25% of that is fly ash. So we've nearly got full fly ash replacement. And in terms of the fine aggregates, we are using a 30% coarse aggregate replacement with recycled concrete aggregate. In terms of the fresh and mechanical properties that we've been able to achieve, I think the important thing in here is that the minimum compressive strength has been able to be achieved with the two optimised mixes, OP1 and OP2. The air contents and the slumps were targeted and very similar to the control mix. The densities varies a little bit, but still similar to the control. The modulus elasticities were a little bit less, and that's probably related to the content of the recycled concrete aggregate in there also, and our indirect tensile strengths were quite similar. In terms of the durability properties, we've carried out tests on drying shrinkage, the apparent volume of permeable voids, chloride ion penetration, carbonation resistance, and water permeability. And you can see the test methods that we have worked towards, and the equipment that was used in the labs at UQ here in St Lucia. And just to show some of the results and not all of the results, the shrinkage performance is a little bit more with the optimized mix designs, as you can see. So the and also the carbonation, I've shown here some of the carbonation values and the bulk electrical resistivity results. The carbonation was measured up to 70 days, and that average depth. It's not all that dissimilar to the control, but there is some variation and difference there that needs to be accounted for. I think that's hopefully I've been able to provide a good overview of a testing or a research framework to follow when trying to characterise recycled materials and optimise mixed designs to fit particular performance requirements. And in terms of the impact that this work has, it shows that the stockpile bottom ash has potential as a SCM replacement for fly ash after proper grinding. Recycled materials are sourced locally, supporting a regional supply chain. Recycled crushed glass and recycled crushed aggregate concrete mixes have been developed that meet pavement performance requirements, and we've been able to have a material savings of 64% of natural sand and 30% of coarse aggregate by volume. And the ongoing research is we're at the last phase of the durability and time-dependent properties, and those concrete mixes will be tweaked a little bit more in terms of improving that time-dependent performance. The concrete, so we've done ASR and leaching tests for the ASR for the sugar, but now we're doing some concrete leaching tests as well that are underway. The life cycle analysis and life cycle cost analysis is also being done at the same time, and we are looking at collecting the inventory, particular for the bottom ash processing. We have a lot of the inventory data already for obviously the other materials, but the inventory data for the recycled crushed aggregates is also another work that we're working on at the moment. And the next stage, hopefully within the next sort of 3 to 6 months, will be the field trials that are planned up here in Queensland and potentially in New South Wales, and that will give us a good idea of how that pavement performs, what its skid resistance is like, and any other sort of abrasion resistance that may need to be monitored, and obviously how to upscale that material to be able to be ready mix delivered. And future work is looking at the fatigue performance assessment of pavements with these types of recycled materials, evaluating the local supply chain, and evaluating the scale up that's needed, and obviously the specification development. And these pictures here that you see here are from a trial that I did for a previous SmartCrete CRC project, where we were using recycled plastic and crumb rubber in those mixes. So which was another successful project also. So hopefully I'll be able to replace these pictures soon with our field trials for this particular road pavement. And thank you for your time, and thanks to all the partners, and they are my contact details if needed, and hopefully that's generated some questions for people that would like to ask.
There's definitely a lot of questions already in the chat.
Oh, really? I haven't read them, so I haven't
That's
seen
fine.
what's
That's
going on.
fine. Thanks for the really good presentation. That's fantastic, and it just shows how much of an academic work or the research work that goes into a product or technical analysis before it gets to even anywhere close to a field trial. And the number of things that needs to be looked at and cross-check against the standards and the multiple trials that comes with it before it gets anywhere near to a field trial and a real case study.
Yes, the concrete labs have been very busy, and as I said, the PhD students and the postdoc have done a tremendous job working on these projects. So yeah, they're to be commended as well.
Yeah. There's already a few questions in the chat, but I'm going to take the privilege of being the chair and ask the first question. I think after seeing all these lab experiments, and I want to come back to what Wayne said in the beginning, for moving from lab scale to looking at a technology which not only works at the lab scale, but also works at a multi-million cubic meters concrete production at a scale. And there is clearly a gap in this space, which is where SmartCrete comes in, try to support. And this is one of such events. So probably the question is, who do we think, I think it's a question for both, very subjective view, is who do you think should fill that gap? Is there an academic overreach that needs to happen to fill that gap, or is that should be filled by private markets, or is there a procurement strategy that come from the government to support this?
Well, I think with I'll just make a quick comment there. I'm sure Wayne can clarify or I think there is a lot of infrastructure that needs to change within the concrete mix process. So it's the capital investment, I think, that might be needed to support those changes. So when we've done some field trials in the past, is we've had to do some hand batching to get the recycled materials in. So it's how the recycle companies are going to handle that recycled material through their process. I think is one of the challenges for the upscaling. But yeah, that's sort of one of my takes. But who takes responsibility for that? I mean, that's where the investment side is a challenge, isn't it? So, and having a material source that's consistent. That's why the material characterization work that has been done is very important. So you know what you're dealing with and what those parameters are, so that you've got a reliable source of material that's not going to change. So you want your recycled concrete aggregates to sit within a particular class or definition, I suppose. But yeah, maybe Wayne would like to add to what I've said from my very academic answer.
Yeah, look, I think there's sort of a couple of stages to it, Aaron. So, there's certainly the academic / lab testing environment is very important in the early stages. Sort of, don't, as Rebecca said, don't underestimate the amount of hard physical lab work that's been done behind the results and the program that Rebecca's presented. So yeah, certainly there's a role for, academic / good laboratory, good hard sort of laboratory work to prove up the concept and to give everybody some confidence that it's going to work. So I think that's definitely the first stage. So, what Smartcrete are doing, what some of the academic sort of research labs are doing, what some of the private company testing labs are doing is certainly a very important first stage. And then I think after that, there is a commercial sort of aspect to it that probably sits with specifiers and commercial concrete companies. And sometimes that just takes time, like getting approval for capex or capital expenditure in the concrete industry, sometimes takes 2 or 3 years for these things to go. I guess the other comment I would make is for a sort of solution to take off in the commercial world, sometimes you need to tick multiple boxes. So, like a bit like I said at the beginning, yes, it has to be technically sound or technically viable, but then it also, it has to be scalable and commercially viable. And you have to tick multiple boxes to get something to take off in the sort of commercial industry sort of world. It can't be just it might be the best technical idea, but if it's not scalable, it's not commercially viable, it doesn't work for the specifiers, or you can't specify it, then sometimes it just doesn't quite take off. But you need to tick multiple boxes along that line. But yeah, certainly towards the end of the process, industry has to sort of, at the end of the day, governments can, or specifiers can, put it in their spec or say it's a good idea. But yeah, obviously, if it doesn't work out in the sort of commercial industrial scale world, then it doesn't work, sort of thing. Would be my answer to your question.
Thank you. I think it's a very difficult question to start with.
Yeah. Yep.
Just
That's
beating
okay.
my own drum.
I'll just add to that. I think that's why when we chose the recycled materials and the suppliers, we looked for local suppliers. We weren't looking for, because I mean, all about the circular economy is to be able to use material that's locally sourced. We don't want to be using material that's imported or anything like that, or that, has to travel from one state to another. So that's what's also unique about this, is that we've really made sure we're using locally, easily available material. So I think the question here is about the repeatability, the consistency in the materials, which we've found to be quite consistent so far. Yeah,
that's the first question from Liam, saying, have you checked the consistency or variability of new materials such as bottom ash, glass, or recycled aggregate?
Yeah. So that we have our benchmarks now in terms of the material performance characteristics, which we can use to know that. But I mean, we've had a couple of suppliers of the materials over, and so far they've been quite comparable. Yeah.
And I think, Aaron, as that sort of recycled material supply chain develops a bit more and sort of grows a bit more, then the sort of consistency seems to be coming. And yeah, again, that takes a bit of time. And for example, a lot of the concrete companies now are collecting their own waste concrete, because that's as an input into that recycling process, because they can actually, you don't have the bricks and the plastics and all the other demolition waste. For example.
Yeah. We looked into a similar sustainable concrete COP in November, talking about returned concrete and how do we process it. Another question from Sam. Sam, asked, given that HB 155 guide to the use of recycled concrete and masonry materials has been withdrawn, is there an opportunity to reintroduce updated guidance to support recycled concrete aggregate and potentially expand the scope of other recycled materials such as recycled glass?
Oh, we have to bring that up with standards, don't we? I don't see why not. Why not? We can't provide some. I'm not across my HB 155. Are you, Wayne?
I can
Yeah.
provide some context. Previously, when we look at recycled concrete aggregate, and we look at what like specification and standards available in Australia, and I found this document that was published in 2002, but it was withdrawn. I think Monash developed. Yeah, Monash developed its guidance. Yeah, but now there's no guidance for us.
Myself and some others were part of a working group to put together a guideline for recycled waste materials in concrete. I don't know where that's at the moment, but there is work in the scenes on trying to develop that with Standards Australia, because we recently the TS 199 was developed, and that was all about geopolymer concretes. And the next stage was the guideline for waste materials in concrete. Boot might know a little bit more about that working group if it's progressed any further. But there was a working group put together with Standards Australia to look at that. We had a few meetings, and I'm not sure where it's gone at this stage.
I think you'll find some of the road authorities now have some specifications in this area. I'm pretty sure there's a recycled glass aggregate type specification on the Austroads website, for example, and I know our concrete specs got a little bit of information on recycled aggregates for N-class concrete, so I think there is some material around still.
Yeah, I'd like to provide some input. Firstly, HB 155. It's quite an old document, but it's actually still very valid in my opinion. I have looked at some of the newer version of the use of recycled concrete aggregates, and really it just demonstrates what was in the HB 155 are still very much relevant. I don't really know why it's been withdrawn. Maybe it need a revision. So that's just first comment. The second comment, I think, Rebecca, you probably refer to a subcommittee in BD2 led by Monash University, I think, to look at the use of, I guess, recycle and waste material. That hasn't progressed sufficiently, I guess, to be included in the revised Australian Standard 3600, which is about to be released for public comment, possibly this week or next week. So that's what I know of this particular subject.
Thank you.
Yeah, I think it's led by Priyan, I think, from memory, that group, right?
Yeah, we had a couple of meetings, but it hadn't gone any further.
No, that's right.
Thanks, Wood, for that comment. And the next question is from Liam. The question is, do you have ongoing tests for durability, or the laboratory specimens or in field trials to get data over multiple years, or any such plans around it?
Yes, so the carbonation testing we finished at 90 days, but the creep and shrinkage is still going on. But if we do a field trial, that's something we could, we probably would look at keeping some of those materials to test over a longer period of time. We find that the creep doesn't really change that much after about 190 days anyway. It really does, and same as so. But it is. I think more would be about the performance in field and going back and doing your site inspections and
Yeah.
as well.
Well, that sounds good, Rebecca. But you did mention ASR testing for the crushed glass and such. ASR takes a long time to develop. Do you have specimens still in storage or something? I'm just hoping you do. I know you probably don't because of lab costs and everything.
Yeah, because ASR wasn't really a big focus of the durability test work, so it's not just the full concentration on the ASR development. So, but yeah, probably not something that we can look at a little bit more in more detail. But at the moment, we are about to do the concrete. So we've done the ASR for the glass and mortar, but now we're looking at the actual concrete mix test. So yeah, see what we got planned
Thanks,
for that.
Rebecca.
But thanks for the input.
Oh, Vert, did you have a response? Did you?
Yeah, just want to provide some comment. Firstly, I think one properties that possibly is need to be known is that of elastic modulus. I referred to HB 155 before, and the most important aspect of that particular handbook is the effect of recycled concrete aggregate on the elastic modulus of the concrete. So I presume that would have been tested because you
Yeah,
need
we showed those results in one of the
Yeah.
tables I gave, and you could see that there was a slight reduction in the modulus with recycled concrete aggregate. Definitely.
Yeah, and the creep test probably would also
Yep.
Taking into effect the elastic modulus as well.
Yep.
The second comment is on the ASR. I presume that work was mainly focused on the effect of recycled glass.
Correct.
On the potential ASR. Liam, you probably be aware that apart from testing for reactivity according to the Australian standards, we are also monitoring field performance, long-term field performance, especially from Canada, and tie that, I guess, to the short-term test results. So I take the opportunity that the Australian standard for mitigation, the two draft standards are about to be released have been released for public comment as well. And that is AS 1141.60.3 and 60.4, the two parts. Sorry, I make use of the opportunity for anyone interested in ASR to perhaps provide some public comment to the committee.
Thanks,
you.
Thanks, Vert. Wayne, did you have a comment as well?
Wayne, you're on mute, Wayne.
Yeah, sorry, I'll get myself off mute. Yeah, I was just going back to context. So in Queensland, we make the assumption that all our aggregates are ASR susceptible and just put in 25% fly ash in all of our concrete. So I guess we're sort of, to some extent, that approach has sort of flowed onto this work, that if we've got our 25% fly ash or bottom ash equivalent in the concrete, that ASR, whether it's recycled aggregate or glass, will be mitigated.
Yeah, that's fair enough, Wayne. I suppose in the future we should test if the bottom ash has the same efficacy.
Yeah, yep, that's a fair comment. Yep.
On the bottom ash, there's another question from Sachi. What processing methods have been done to bottom ash? Have you considered, or do you have plans to explore how processing bottom ash affects overall carbon reduction in concrete? Yeah. I remember you mentioned ball mill, Rebecca.
Yeah, so we've used a ball mill to grind the bottom ash for 15 minutes, and that's for not a relatively big quantity, and so our LCA modelling will need to take that into account when we do those calculations. So I don't have quantitative values to let you know what that carbon reduction is or what impact that has on that carbon reduction at this present time, but that will be part of the final work as well. But thanks for the comment.
I would assume that has a lot of different parts of how we dig up the bottom ash and how we transport it. It has to develop for completely, I would assume.
Yeah, that's right.
Yeah.
So the bottom ash is, this particular bottom ash is coming from near Gladstone, so there's transportation costs
Yeah.
and distances to consider as well.
Mm.
Yeah, there was a drying process as well. So yeah.
Yeah. Another question from LND. Great presentation. Thank you so much for Rebecca and Wayne. And there are any plans for future research on the use of recycled concrete aggregates in structural concrete applications as an extension of this work? Regarding durability testing, any planned test on long-term chloride diffusion testing?
Yeah, so the recycled aggregates, I think, is the next hot topic for structural applications. So yes, there will be plans for lots of people, not just myself, I'm sure. This is only a 3-year project, so part of this project we will probably stop with that side of the work, but I think once we've optimized our mixes, then separately we will run some other longer term durability testing as needed.
I guess from my point of view, Aaron, this project is nominally focused on a sort of S40 or special class 40 MPa concrete, and because of the sort of Transport for New South Wales funding focus, that's obviously can be used in pavements. But it's most of the work that's been done is also probably transferable to sort of a 40 MPa structural cast in situ concrete application. So in a TMR world, that's sort of, chloride diffusion is probably not as critical because we don't use that sort of concrete in a chloride type environment. We would sort of step up to a 50 MPa sort of mix. So yeah, I guess, yeah, this is potentially a step on the way to getting it into sort of S40 structural type concrete, columns, headstocks, in sort of, normal exposure class where you're just looking at probably carbonation is the most critical exposure class. And then, then there obviously is another step up to sort of 50 MPa concrete where we'd be starting to look at, pre-stressed concrete girders and exposure class C type. That's probably another big step up after that sort of thing. But yeah, probably the majority, by volume, the majority of concrete we use would be that sort of S40 type concrete in a, normal, relatively normal exposure class, B1 sort of type thing.
Yeah, thanks for that, Wayne. That's a really good answer. And I think I also understand there's a lot of steps involved in between where we are now and where we are getting to a structural in-cast in situ application. And I work for precast, and I look at we are further away. Once we get in situ applications and a few successes, then we talk about, okay, can we do this in a precast world and get the early edge strength supportive to a commercial reality. And but everything said and done, it's a really good presentation from both. So thank you, Wayne, and thanks, Rebecca. It's bringing anything. I think if anything, it shows very clearly how difficult it is to bring a new technology and how much rigor of work that go into bringing a new technology into practice. And it's for the great job that you have been doing for a long period of time. Thank you for both of you. And for Smart Grid point of view, if you have any questions or if you have any follow-up questions or interested in collaboration opportunities, please reach out to Smart Grid CRC. It'll help you connect with the right people. And that is it from us today. And thank you again, and enjoy the rest of your day.
Thank you, everyone.
Thank you.
Bye-bye.